morning class and welcome to our lectures in sustainable energy technology. We were discussing fuel cells as a method of converting hydrogen directly into electricity. And we were looking at multiple types of fuel cell systems with a brief description of each of these types. So for example, we discussed alkaline fuel cells, which uses, for example, KOH as an electrolyte. Then phosphoric acid fuel cells, which uses phosphoric acid as an electrolyte. Then molten carbonate fuel cells, which uses molten carbonate salts like sodium carbonate, lithium carbonate, etc. as electrolytes. We also discussed solid oxide fuel cells, which uses yttria stabilized zirconia, a kind of solid oxide, as the electrolyte, and it operates at higher temperatures, making it ideal for stationary power generation systems, reasonably large scale stationary power generation systems. One of the most common and popular types of fuel cells nowadays is the PEM fuel cells, which is basically proton exchange membrane fuel cells. So these types of fuel cells are based on sulfonated tetrafluoroethylene membrane, which is a moist Nafion membrane that can transport H+ ions. We discuss some of the advantages of PEM fuel cells because it can work at temperatures below 100 degrees centigrade and has high power densities, low specific weights, and good stability. We also discuss certain variants of PEM fuel cells. For example, the high temperature PEM fuel cells, which can work at 200 degrees centigrade using mineral acid instead of moist PEM. And we also discuss direct methanol fuel cells, which is a variant again of this PEM fuel cells, where instead of platinum we use platinum ruthenium catalyst, which can directly convert methanol into electricity instead of using hydrogen. In this lecture today, we will start by discussing the working principle behind some of these fuel cells to get a better picture of how they actually work. So for the phosphoric acid fuel cells and the PEM fuel cells, both of them work on a very similar principle in that their electrolyte basically transport hydrogen ions like H+ ions or protons from one electrode to the other electrode. Okay. So in the anode reaction, you have hydrogen breaking down into H+ ions and electrons, and in the cathodic reaction, which is happening here, this H+ ions that is being transported from the anode to the cathode is reacting with oxygen to produce water vapor and absorbing electrons in the process. So what is going on there is then at the cathode, air is coming in and water is coming out. It can be water or water vapor based on the operating temperature we are looking at. For typical PEM fuel cells, which are operating at around 80 degrees and 90 degrees, it will be hot water that is coming out. For high temperature fuel cells, for example, phosphoric acids that are working at a somewhat higher temperature, you will get water vapor in the system. And on the fuel side, you are getting hydrogen and it is getting absorbed at the anode, and the excess fuel is removed. Okay. Usually nothing is coming out. If exact same amount of hydrogen is given, then nothing comes out from the exit side. Okay. And the electrolyte changes. So for example, in the phosphoric acid fuel cells, you are using a dilute phosphoric acid, while in PEM fuel cells, you are using moist polymer exchange membranes. Okay. The molten carbonate fuel cells works on a different principle in that it is basically transporting carbonate ions, CO3 2-, from the cathode side to the anode side. Remember, we are defining cathode is one where electrons are being absorbed and anode as the one where electrons are being released. An electrical current is flowing through the external circuit between the anode and the cathode. So this is the transport of electrons and this is the transport of current. Okay, because cathode is basically absorbing the electrons and anode is generating the electrons. So the flow of electrons is in this direction, but the current is moving in this direction. Okay. Anyways, here what is happening is in the anode side, you can have several types of reactions happening. So for example, if you are using syngas, which contains a mixture of carbon monoxide and hydrogen, so suppose syngas is coming in, then both H2 and CO will be there, and this is basically reacting with the carbonate ions that is transporting from the cathode towards the anode side to produce CO2 and water vapor in the case of hydrogen. The CO is reacting with the carbonate ions to produce 2 moles of CO2 and electrons, whereas hydrogen is reacting with the carbonate ions to produce water vapor, CO2 and 2 moles of electrons. These electrons are getting transported through the external circuit and going towards the cathode. In the cathode reaction, you are actually transporting oxygen and CO2. So oxygen is coming in from one side and CO2 is coming in from the other side, and these two are reacting with the electrons coming from the external circuit to form your carbonate ions. Okay. So let us understand this system a little bit more carefully. What is happening here then? Suppose you have, let's look at the simple case where you are pushing in pure hydrogen. If pure hydrogen is going in, then this first reaction is happening in the anode and you are getting out water and CO2. Okay. So water is coming in, water is being taken out, and the CO2 is being transported through an external pipe, for example, and is being flown back towards the cathode side where this CO2 will be needed. Okay. Now at the cathode side, you are taking in oxygen from air, and this oxygen and the CO2 that is being circulated from the anode side are coming together and producing the carbonate ions, and this carbonate ion is flowing through the system. Okay. So CO2 produced at the anode has to be separated and directed back towards the cathode to prevent electrolyte loss. Okay. So you have to be careful that you have to recirculate this CO2 back. Otherwise, if you are not recirculating the CO2, you have to get an external supply of CO2. Otherwise, the electrolyte will slowly get exhausted. Okay. So this is the molten carbonate fuel cells. Now if you look at the SOFC fuel cells, where the electrode is strontium doped porous lanthanum manganese oxide, and the positive electrode is this one, and the negative electrode is the porous ceramic and metallic materials like cermets. Okay. So here in the anode reactions, what you are having is hydrogen is reacting with oxygen ions. So here what is happening is oxygen ions are getting transported from the cathode side towards the anode side. Alright. Remember here, since the electrons are flowing this way, the positive electrode is this one, the cathode, and the negative electrode is this one, the anode. Okay. So here at the anode, you are absorbing, say, hydrogen, which is reacting. You are taking hydrogen from the external flow. This is reacting with the oxygen ions that is coming through the electrolyte to produce water vapor and releasing electrons. These electrons are flowing through the external circuit and going to the cathode. In the cathode, oxygen of air is reacting with the electrons to produce the oxygen ions, and this oxygen ions is basically being transported to the solid oxide structure of the electrolyte, which is yttria stabilized zirconia. Okay. And you have the positive electrode as the strontium doped porous lanthanum manganese oxide, and the negative electrode is a porous ceramic and metallic material called cermets. Okay. And this is usually a high temperature reacting system. One of the advantages of a SOFC is it can handle multiple types of gases. So if it's CO, then it is producing CO2 plus the electrons. If it's methane, it is producing water vapor, CO and CO2 and the electrons. So it can work both with hydrogen, CO and methane, and unlike say the PEM fuel cells or the PAFC fuel cells, or the KOH fuel cells, this is not poisoned if hydrogen is not pure and contains hydrocarbons. Okay. So that is the basic operating principle of the three types of main fuel cells that we are discussing here. So here we finally look at the comparative analysis of the various types of fuel cells and their advantages and disadvantages. So all these fuel cells are commercially available. The size range, however, is quite different for different types. So for example, the alkaline fuel cells, the maximum power you are getting is up to 100 kilowatts. For the phosphoric acid fuel cells, you are getting around 400 kilowatts. And for the direct methanol fuel cells, you are getting up to 5 kilowatts. So this is the smallest of them. So it is very small portable electrical device. These can go to small, you can have portable systems to medium scale electricity generation systems using AFC and PAFC. In contrast, the solid oxide fuel cells, the molten carbonate fuel cells and the PEMFC fuel cells, the PEM fuel cells, can go from 1 kilowatt. So SOFC, for example, is certainly these are going from a 1 kilowatt range to 10 megawatt range. The molten carbonate fuel cells have to go even bigger, 250 kilowatt to 10 megawatt range. The PEM fuel cells can go to small values, 3 kilowatts to up to 1 megawatt range. So PEM fuel cells is kind of going from medium scale power generation to large scale power generation. Similarly, for SOFC fuel cells, the MCFCs have to be very large scale power generation systems. Okay. Typical operating temperature is also different. The under brackets is the degree centigrade values here. So this is 250 degrees centigrade, the alkaline fuel cells. The phosphoric acid fuel cells work at 200 degrees centigrade. The SOFC fuel cells work best at 1000 degrees centigrade, so it's the highest temperature among all of these fuel cells. The MCFC fuel cells work at 650 degrees centigrade. The PEM fuel cell is a close to room temperature, around 90 degrees centigrade. Similarly, DMFC is going at 90 degrees centigrade. So you can see from the temperature profiles why the PEM fuel cells is very good, because it is operating at close to room temperature ranges, and you do not need an extensive thermal management system as you would need for SOFC and MCFC systems, and you are still getting large scale power generation. The fuel has to be pure hydrogen for alkaline fuel cells. This is also true for regular PMFC fuel cells, but if you are going for high temperature fuel cells, high temperature PMFC is at 200 degrees centigrade, then you can go with other types of fuels as well. DMFC is specifically for methanol. One advantage of SOFC and MCFC is it can work with natural gas, hydrogen, landfill gas, fuel oil. So SOFC is one of the most versatile. PAFC is also reasonably versatile. Okay. MCFC also can work with natural gas and hydrogen based fuels. Okay. Hydrogen is the best for all of these cases, but for SOFCs, MCFCs, certain types of PMs and certain types of PFCs, you can go with other types of hydrocarbons as fuels as well. Though keep in mind that if you are not generating methane, natural gas, for example, is not a renewable resource. So here you are then using the fuel cell as a non-renewable fuel to power generation device, but still it is quite efficient. So in that way, you can increase the efficiency of existing power generation systems by shifting from a combustor to a fuel cell under certain conditions. So this is the next point then, the efficiency of these systems. So for example, the PEM fuel cell goes from 35% to 60%, so it can go to lower efficiencies as well depending on what type of PEM fuel cell is being used. DMFC is the least efficient of these fuel cell systems, it's around 20% to 30%. SOFCs and MCFCs and AFCs, these have high efficiencies, 50 to 60%. So these stacks, so it's not the theoretical efficiency we are talking about, the actual technical efficiency we are getting after going into the fuel cell stacks proper. Okay. So these have high efficiencies of 50 to 60%. The PFCs have a somewhat lower efficiency of 40 to 45%. Okay. Reforming is basically what is needed if you want to create hydrogen from hydrocarbon resources. So you have to have an external reformer to handle the to convert the hydrocarbons into pure hydrogen. Okay. So many of these fuel cells, apart from SOFCs, for example, and MCFCs, require an external reformer to handle this non-hydrogen based fuels. Okay. So basically, in your fuel cell, you are still putting hydrogen. It's only that you are generating hydrogen in an external facility, and that way it can handle other types of fuels. This is true, for example, the PFC fuel cells and PEMFC fuel cells. Okay. They require the external reformer because they have to deal with hydrogen as the final source. Okay. So this, of course, decreases the efficiency somewhat. Okay, because you are basically losing out on the energy of the carbon that is there also. SOFCs do not need a reformer. You can have it, but internally it can handle the gases. So that's why it says internal reformer. Okay. Similarly, MCFCs do not need a reformer. You can handle the gases directly in your system. Okay. Another important point regarding the cost analysis also is whether you need a noble metal catalyst. Noble metals are expensive and the resources are not significant. So this is important because if you want to deploy fuel cells at a very large scale in the future, this noble metal catalyst can become a bottleneck. So AFCs and PAFCs require platinum or palladium based catalysts. SOFCs do not, so that's an advantage for them. MCFCs require nickel or nickel oxide catalysts, which is which is reasonably well available. So unlike platinum, palladium or ruthenium, this is reasonably well available. PMFCs require either platinum or ruthenium. So platinum is very expensive, ruthenium is less expensive. So we are shifting to ruthenium based catalysts nowadays to decrease the cost of PMFCs. Similarly, DMFCs require either platinum or ruthenium. And all of these have nearly zero emissions, with a caveat that if you are using hydrocarbons, then emissions will be there. Okay. So that's the kind of the comparison of the various fuel cell types and where what is used. So if you want large stationary storage, large energy generation systems using fuel cells on the stationary scale without requiring any catalysts and have good compatibility with various types of fuels, then you should go for SOFCs. However, if you want to go for a more versatile kind of a fuel cell that can go to large range and medium range and can work at room temperature, so that there is not a significant thermal regulation system that you need to generate, and you can get a reasonably pure stream of hydrogen through an external reformer or directly, then you should go for PMFC based fuel cells. So PMFCs are extremely compatible with specifically hydrogen infrastructure. So that is why people are looking at this as a very good way to convert the energy in hydrogen into electricity using the PMFC fuel cells. So that kind of ends our discussion on the fuel cells. We will briefly start the discussion on the next and the final stage that we will discuss. This is carbon capture and storage, CCS technologies. Okay. So we are now shifting from energy storage based technologies to sustainability technologies, and this is the most important technology that can decrease the carbon intensity of existing fossil fuel infrastructure, energy infrastructure. Carbon capture and storage. Okay. So this will improve the sustainability of the existing fossil fuel infrastructures. The fossil fuel infrastructure will still remain a non-renewable resource, but if you can properly capture the CO2 that is being emitted and store it safely, then the CO2 intensity of that fossil fuel infrastructure will be a lot less, and that would increase the sustainability of such an infrastructure in the future. So CCS technologies is a very important aspect of how to improve the decrease the carbon intensity or the CO2 emissions that are being generated per unit of energy from our existing fossil fuel systems. Okay. So this to motivate our cause, I am just giving excerpts from the IPCC's 6th assessment report that was released like 1 to 1.5 years ago. Okay. So these are excerpts from the mitigation report, climate change, how to mitigate climate change, and they highlight the importance of CCS technologies over the short, medium as well as long term to actually deliver a below 2 degree warming scenario, okay, to decrease the carbon intensity of the energy industry. Okay. So what it says is net zero CO2 energy systems entail a substantial reduction in overall fossil fuel use. So this is the first strategy. We reduce the use of fossil fuels like natural gas, oil, coal, etc. by creating renewable energy infrastructure, renewable energy storage infrastructure, an advanced grid that can take greater extent of penetration of renewable energy into the system. So this has been discussed extensively till now. Okay. Minimal use of unabated fossil fuels. So fossil fuel technologies that cannot be improved in terms of efficiency or sustainability, we do not use them. Okay, we find alternative routes. Okay. And use of carbon capture and storage in the remaining fossil fuel systems. So in the existing fossil fuel systems that cannot be replaced, you use and implement carbon capture and storage based technologies to decrease the CO2 emissions from them. Okay. So this is the three-pronged strategy: reduce overall fossil fuel use, minimize use of unabated fossil fuels, and use CCS in the remaining fossil fuel systems. Another point that was highlighted in the IPCC 6th assessment report on mitigation is limiting global warming to 2 degrees centigrade or below will leave a substantial amount of fossil fuels unburned and could strand considerable fossil fuel infrastructure. So today we have a large fossil fuel based energy infrastructure in the world. You have large coal power plants, large oil wells, IC engine technologies for the transportation systems, large scale natural gas power plants, natural gas based heating systems and heating technologies. To limit the global warming to 2 degrees centigrade or below, we have to quickly shift to renewable energy technologies, and all of these technologies which had 30-40 years lifetime left in them will have to be closed or shut before their lifetime gets over. Similarly, all of these oil wells, gas wells, coal mines which had a large amount of resource and financial capital invested in them will be idled. Okay. People have invested resources in them, people have invested resources in these technologies. These power plants were developed for considering a 30-40 year lifetime. Now if we shift to renewables, all of these will have to be shut down before their time and before their economic costs can be are recuperated and profits have been made from selling the energy or commercializing that technology. Okay. The combined global discounted value, you don't have to worry about what is the global discounted value means. It's basically the combined value of the unburned fossil fuels and stranded fossil fuel infrastructure has been projected to be around 1 to 4 trillion from 2015 to 2050 to limit global warming to approximately 2 degrees centigrade. So the total expected unrecuperated cost that will be stuck in this fossil fuel resources and fossil fuel infrastructure in which people have already invested in is around 1 to 4 trillion dollars. Okay, which is a huge number. Okay, so if we shift to renewables, this is an economic cost that has to be borne by the existing fossil fuel industries and the fossil fuel resource managers and the companies. Okay. So what is the solution to this? Is there a solution? Can we decrease the losses here? Okay. Depending on its availability, CCS could allow fossil fuels to be used longer, reducing stranded assets. Okay. So high confidence means there is a good confidence that if CCS technologies become mature, then it will be possible to reduce these $1 to $4 trillion losses significantly by using CCS and developing carbon neutral ways of utilizing these fossil fuel resources and technologies. Okay. This will also decrease the economic cost and hence will have a lesser effect on the global economy. Alright. The last point, and I will stop today here on this front, is that the technical geological CO2 storage capacity is estimated to be on the order of 1000 gigatons of CO2. So the estimated technically feasible geological CO2 storage capacity, so it has to be stored somewhere. Is there enough place for it to be stored? That's the next question, right? Is around 1000 gigatons of CO2. So we can store with the given expected technological development around 1000 gigatons of CO2 in the available geological reservoirs, which is more than the CO2 storage requirements through 2100 to limit global warming to 1.5 degrees centigrade. So what this means is there is enough geological reserves available to store around 1000 gigatons of CO2, which is sufficient for the projected CO2 storage requirements for the CCS technologies up to 2100 to meet our global warming targets, even the most stringent target of 1.5 degrees centigrade. So it is possible to do this. There is enough space available to have this CCS technology work. One problem is regional availability of geological storage could be a limiting factor, because CO2 is being emitted by different power plants, but the geological storages may be located in some places and not in other places. So there is a concern of how to transport the CO2 to the place where geological storage is happening, and we will discuss the transportation options later in the class. But that is a concern, that it's located in places where there is not much emissions, and there are places where there is a lot of power plants emissions, there isn't enough geological storage. So that problem remains. If the geological storage site is appropriately selected and managed, it is estimated that CO2 can be permanently isolated from the atmosphere. So this is the second concern, right? That if you store CO2 in underground reservoirs, will it eventually leak out? And if it does, then the problem remains, right? You are basically just shifting maybe 5 to 10 years down the line what is the effect of the emissions. That is not useful. Okay. There are other concerns with CO2 leakage as well that we will discuss later in the class. But what IPCC says is, if the storage site is appropriately selected and appropriately managed, then this CO2 will always remain underground and it will not seep back out into the atmosphere. Okay. So it is possible to safely store this indefinitely. So with that idea that it is possible, there is potential, we will stop this and we will look in the next class on the technologies of CO2 capture first, then CO2 transportation, and finally where to store it and how to store it. Okay. Thank you for listening and have a good day. We will meet in the next class.